Okay, this is a discussion of area under a curve. So our directions here are going to be to find the area under the curve. And we're just going to call any graph that we have, we're going to call it a curve, even if it's a straight line. Okay, so find the area under the curve and above the x-axis, that's important as well, above the x-axis, on the given interval for each of the following functions. Okay, so these first couple are going to be pretty easy. Our function is f of x equals 2. I have that graphed. It's just a horizontal line at 2. Right, y equals 2. I want to think about the graph just from 0 to 4. My interval is from 0 to 4. So I'm going from here to here. Those are x values. So what is the area under the curve from 0 to 4 and above the x-axis? So essentially what I'm trying to find is this area right here. Now the nice thing about this is it made it a geometric shape, right? So if I wanted to find the area of this, my length of my rectangle would be 4, the height of my rectangle would be 2, and so very simple formula here, the area is going to be 8 square units, because I can just think of that as a length times width. It's a rectangle, 4 times 2. Okay, number 2, we have a function that's f of x equals x. So it's a diagonal line through the origin, slope of 1. We're going to go from 0 to 4. So I want to look at this region right here from 0 to 4, the area under the curve, but above the x-axis, would give me this area right here. So how do I find the area of that? Well, this time it made a triangle. The base of this triangle is 4. The height of this triangle is 4. The area of a triangle would be 1/2 base times height. So again, we're going to get 8 square units. Okay, pretty easy so far. Well, the question becomes, what do we do if our graph doesn't give us a nice geometric shape? So now we have 1/4 x squared. We're going from 0 to 4. And so now I want to try to find this area under the curve here above the x-axis. But that's not a geometric shape. That's not a triangle, right? It's kind of like a triangle, but we've got a curved side there. So it's kind of, how do I use a geometric formula to figure that out? And the answer is you can't. Okay, so we're going to start talking about how do I find that area without using a geometric formula. So what we're going to do here is we are going to, for this sake, we could estimate it. Now again, an estimation just by kind of looking at it and kind of counting boxes is not going to be very accurate. So what I mean by that is, yeah, I could give like a quick estimate of what this would be. This is 1 unit. If you look at the numbers there, that would be 1 square unit. Here I have another square unit, so that would be like 2. Here I have another square unit, so that would be like 3. But then I start to have these boxes where I don't have a complete box here, right? So like maybe I could say, well, maybe if we took this one right here and this one right here, and I kind of added those together, maybe those together would give me 4 units. And then maybe I could take, I don't know, this one right here with this one right here, and adding those together, that would be pretty close to another unit, and that might give me 5. And then, oh, well, I've still got this little part right here that I haven't talked about yet. So is it 5 point something? I don't know. I could kind of give a rough estimate of what that might be. But we don't want to do that. Okay, so we're going to look at some methods for how we can figure out how we can give a nice, good estimate of what that would be instead of just trying to count boxes. Okay, that is not the method we want to use. So here's what we're going to do. We can estimate the area under a curve using rectangles. So we are going to determine the height of the rectangles we're going to split our interval up into n number of rectangles. So however many rectangles we want to make, we can make a bunch of rectangles underneath here. What we're going to do is determine the height of these rectangles by either using the left endpoint or the right endpoint of my subintervals I'm saying, well, if we split this from A to B into 4 rectangles, I could use maybe my left endpoint of each one to determine the height of each one of these rectangles. So if you look at this, notice the height of each one of those rectangles is determined by the value of the function at the left endpoint of that interval, right? So every single time, it's whatever my left x value in each one of those intervals is. I could use my left endpoint. I could also use my right endpoint. So this next one is showing right endpoints where my first interval goes from a to x1, and I'm using the value at x1 to determine the height of that rectangle. And then from x1 to x2, I'm using the height at x2 to determine that rectangle. Now, hopefully you see with both of those cases, we don't have great estimates because our left endpoint is giving us an underestimate of what that would be. We've got space that we are not including underneath the curve. Our right endpoint in this case is giving us an overestimate because all of our rectangles are slightly above the curve, so I'm going to end up with an estimate that's going to be too big. So we could also use midpoints. So the idea here is for this rectangle that goes from A to x1, if I were to take the x value that's right in the middle of those, and I go to the function at that x value, that can determine the height. And then go halfway in between x1 and x2, and that could determine the height. And so forth. And notice how when you do a midpoint, your estimate is going to be the best because we're going to have a little bit of additional area that we're including that's not under the curve, but we're also going to have a little bit of area that we are not including that is under the curve. And so theoretically, those will cancel each other out and give us a, not completely, but give us a very close estimate to what that might be. Okay, what the area under the curve might be. So here's kind of the mathematical explanation of what I just said. The idea here is that if I were to make my rectangles, the number of rectangles, that's what n is, the number of rectangles go to infinity, that would mean I want to make as many rectangles as I can underneath my curve. And if I could do that, if I could just put an infinite number of rectangles, then the amount of space that we are missing, the amount that we're going above or that we're missing below, will become negligible. Because those rectangles are going to get so skinny that they're going to pretty much follow the curve all the way from A to B, right? And I'm not going to have this excess area or this missing area. And if I make more and more and more rectangles, I'm going to get a closer and closer estimate to what that actual area is. And that is what this tells me. The second part of this is telling me that the width of each rectangle would simply be to do the difference in your interval. So A to B, if I do B minus A, and I divide by the number of rectangles that I want, that would tell me my change in x, or the width of each rectangle. Okay. So we're going to look at an example here where we have the curve f of x equals x squared. So I have that drawn here. I want to go from 0 to 4, and I want to use 4 rectangles. These rectangles also need to have equal width, which you will be using when you do this. So equal width, 4 rectangles from 0 to 4. And I'm going to do the estimate using left endpoints, using right endpoints, and using midpoints. Okay, so if I go from 0 to 4, and I use 4 rectangles, the width of each one of those, using this formula right here, which should be pretty easy, should be kind of self-explanatory what the width would be. But the width of each one of these, delta x, is going to be 4 minus 0 divided by the number of rectangles that I want, which means my rectangles would all have a width of 1. And that should make sense. If you go from 0 to 4 and use 4 rectangles, they are all going to have a width of 1. Now, how do I determine the heights? And that's going to be determined differently based on left, right, and midpoints. So, to kind of help you visualize what's going on. My first rectangle would go from 0 to 1. And if I were using left endpoints, what that means that I want to do is my rectangle that goes from 0 to 1, I want to use the left endpoint of that interval, which would be 0. And the height of that rectangle is determined by what the value of the function is at 0. So here's my function, f of x equals x squared. At 0, the answer to that is 0, which means this rectangle has no height to it, right? So my first rectangle would have a width of 1 and a height of 0. And I'm going to add to that, and again, that's area of that rectangle, right? That's width times height. So that's going to be the area of the rectangle there. My next rectangle would go from 1 to 2, and if I'm using left endpoints, then I'm going to use my endpoint at 1 to determine the height of that rectangle. Right? So I'm going to have this rectangle right here. And again, using left endpoint, so from 1 to 2, use the 1 to determine the height. So the width is 1, and the height is 1 because this function, when evaluated at 1, is 1. Plus, the next one would go from 2 to 3. Determine the height at 2, and make your rectangle. So my height at 2 would be 4. Because, again, the function evaluated at 2 would give me 4. So the width is 1, and the height is 4. And then I'm going to have one more rectangle, and that's the one that goes from 3 to 4. And again, we're using left endpoint, so I'm going to determine the height of this rectangle by using 3. Make that go straight across. And I want to find the area of this rectangle. So that would be width 1, height is 9. And again, I'm using that formula there. Now, I hope you can see that this is an underestimate, right? Because I've got space here that I'm not counting. And again, we're supposed to go all the way to 4, so we're missing all this space up here too. But it's an underestimate, right? But what I have is I have 4 rectangles. An area of a rectangle, an area of a rectangle, and so forth. I have 4 of those. And what I'm going to do is add all those together, and that would give me 14. So my estimate for the area under the curve using left endpoints is 14. Now, I can do this all over again using right endpoints. So I'm going to kind of do the same thing, except now to determine the heights, I'm going to use the right endpoint of each interval. So the interval from 0 to 1, I'm going to use the height at 1, and that's going to be my rectangle that I draw. So my first one is width 1, height 1. My second one goes from 1 to 2, and I'm going to use the height at 2. I'm going to use the right endpoint to determine that area. So that's going to be width 1, height 4. Plus, from 2 to 3, that's going to be a height of 9. So width 1, height 9. I use 3 to determine the height. From 3 to 4, this time I'm going to use the height at 4, which is all the way up here at 16, because again, 4 squared would give me 16. So width 1, height 16. And if I multiply all of those width times height, I get all my areas, I add all those together, that gives me an estimate of 30 square units. Okay, so we said before that left and right hand endpoints are typically going to give us overestimates and underestimates. Now, if the function is a decreasing function instead of an increasing function, then those would be flipped. The left endpoint would give you an overestimate, and the right endpoint would give you an underestimate. But what I can do now is I could find the midpoints of each one of these intervals and find my heights based on those midpoints. So if I did that, here's the idea. From 0 to 1, I would want to find the height of the function at 1/2. And that would determine my first rectangle, right? Because the midpoint of that interval would be 1/2. And then from 1 to 2, I would find the height at 1.5, and that would give me this next rectangle. Now, those values aren't as easy to get as these were, because my function x squared is pretty easy to evaluate at whole numbers, right? Small whole numbers. Now, so just to show you what this is going to kind of look like, what I could say is, well, what I'm really doing is I'm doing 1, and then I'm going to do times f of 0.5 plus 1 times f of 1.5 plus 1 times f of 2.5 plus 1 times f of 3.5. So what's that saying? That's saying that my width every time is 1, and my height is determined by the function's value at 0.5, the function's value at 1.5, at 2.5, and 3.5. Those are all of my midpoints of my intervals. And so, what's that look like? That looks like 1 times 0.5 squared plus 1 times 1.5 squared. And again, this is because my function is x squared, plus 1 times 2.5 squared plus 1 times 3.5 squared. And if you evaluated all those, add them all together, you get 21. And 21 is going to be a better estimate than 30. That was too much. 14 was too little. We are not saying that 21 is the correct area. We are just saying that it is the closest estimate because I used those midpoints instead of left or right endpoints. Okay, so using those rectangles to determine those areas is going to be an important skill moving forward, and we want to make sure that we know how to do left, right, and midpoints, and what that means if I'm given a function, and how do I evaluate those heights given that function. Okay, just to show you really quickly in Desmos kind of what we were doing here. This is maybe a better than my drawing, better representation. So again, we've got our function is x squared. We're going from 0 to 4. In this case, we're using left endpoints. So my first one is 0 to 1. My height is determined at 0. Then from 1 to 2, my height is determined at 1, and so forth. So this was our left endpoint. This was our right endpoint. 0 to 1, height 1. 1 to 2, height at 4. 2 to 3, our height is 9, and so forth. And then we can also look at our midpoints, and this is what our midpoint would look like. And again, this is the best estimate because I've got a little bit above the curve, a little bit under the curve that we're missing, and those will theoretically come pretty close to canceling each other out to give us a value here. So that's kind of visually what that looks like. Again, probably a better representation than what I was able to actually draw. So again, if it is a nice geometric shape, I should mention that again. If it's a nice geometric shape, by all means, use a geometric formula to figure that out. Don't draw these these rectangles underneath here. Just use your geometry formulas, and that will help with that. But if your shape is not a geometric shape, we're going to estimate that using these rectangles.